Okay, this video will contain solutions to section 8.3.
So this is section 8.3 solutions.
Now, I'm not going to do every homework problem, but I'm going to just do a sampling of some of the homework problems that were assigned.
So I'm going to begin with problem number 9. Problem 9 says use the comparison test to determine whether the series is convergent or divergent. And the series they give us is n equals 1 to infinity of n divided by 2n cubed plus 1.
Now, when we're trying to use the comparison test, we have to focus on the known series that we have, our what I call our catalog of series.
So remember, it's not very big. We have the harmonic series. We have geometric series. And we have P series. Later, we get to the alternating harmonic series.
But we don't have that one right now because we're still in section 8.3, and in 8.3 we haven't seen the alternating series that come up in section 8.4. But we'll just put it down for now. So when we have a problem and they tell us, as they did in this problem, to use the comparison test, we have to think to ourselves, all right, what can I compare this to? Now, remembering, of course, that if we can make this smaller than something that converges, right?
So on this side, let's just think about it this way. If we have convergence over here,
you know, there's a series and it converges,
and our series is smaller,
then we know our series by the comparison test must converge because it's smaller than a series that we know already converges. So the secret to doing these problems is to just practice, because we have to come up with something that looks like this.
and so we start by playing with this, right? We take our general term,
and we ask ourselves, okay, what do we know? What do we know about this? Well, it's a fraction. We know when we make the denominator bigger, we added 1 here, for example. When we make the denominator bigger, we make the fraction smaller.
So if we were perhaps to not make the denominator bigger,
we'll get rid of the 1. We know that this is bigger than this because when the denominator increases in a fraction, the fraction becomes smaller. But this is equal to this. Just doing our math,
which is really just 1/2 times 1 over n squared.
right?
But this person
Looks like a P series. So this is how we play the game to try to develop a series that we can use in the comparison test. So what we can say right now, without a doubt,
is we can say this is true. Our series, because of what we've established up here, is less than this series. Now that's a half, that's a constant, that can come out in front.
But this series is a convergent P series.
since P is equal to 2, which is greater than 1. Therefore, by the comparison test, our series converges. Now, before we can use the comparison test, right, we have to satisfy the hypothesis. Now, there's only one hypothesis for the comparison test, right? There's just one hypothesis. Here, back here at the beginning, we would have to show all terms are positive. But we know n goes from 1 to infinity. And since n is always positive, n cubed is always positive. So n cubed plus 1 is positive, n is positive. So this satisfies the hypothesis for the comparison test. It has all positive terms. And we've found a series that's bigger than ours that converges. And so since it's larger than ours and it converges, we don't know what ours converges to, but we know it must converge. Okay, so let's take a look at number 10. That was number 9. Let's go ahead and take a look at number 10. It's the same set of instructions, right? And here we have sigma n equals 2 to infinity. And we have n cubed over n to the 4th minus 1. Okay. So if we take a look at this, right? If we take a look at this, we ask ourselves, well, what does this look like? We kind of got the idea from here. We had n to the 1st here, we had n cubed down here. So we thought, well, we should try to look for something in the neighborhood of n squared. You know, we have an n to the 1st, n to the 2nd. We should try to think about trying to work n squared into this. Well, here we have n to the 3rd, n to the 4th. So if we play the same relationship game here, we had a 1 and a 3 that got us a 2. Here we have a 3 and a 4. It's going to get us a 1. We know that that's going to be our friend, the harmonic series. So, you know, we're thinking this might diverge, but we haven't done the work yet. So n starts at 2. We put a 2 in here, we get 2 to the 4th is 16. That's positive. 2 to the 3rd is 8. That's positive. So this, all terms are positive. We want to write that down to show that we've checked the conditions for the comparison test. We don't want to just leave that blank and allow someone to assume that we didn't know that was supposed to be checked and therefore we didn't do it. By writing it down, we can establish we've looked and we've satisfied the conditions. So now we're going to take our friend, you know, n cubed over n to the 4th minus 1, and we're going to say what? What do we know about this? Well, we know this is less than, right? Less than. Well, do we want it to be less than though? So we've thought about, right? Our thought over here was, well, we should do this. We should do this. This diverges, doesn't it? If the known series diverges, does it do us any good to show that we're smaller than that? Or is it the case that we want to show our series is greater than that, right? That's what the comparison test says. The comparison test says if our series is bigger than a series that diverges, it's bigger than something that diverges. This goes to infinity, and we're bigger than that. Well, then we must follow along and go to infinity as well. So when our thought is divergence, now we may turn out to change our mind, but when our thought is divergence, we want to show that this is bigger than something else. Well, this is bigger than this.
Because when we make the denominator, we subtracted 1, right? When we make the denominator in a fraction smaller, the fraction gets bigger, right?
If we have 1/3 and we take away 1, then we didn't make a fraction that's smaller,
We made a fraction that's bigger, right? So when the denominator gets smaller, the fraction gets bigger. So here we took away 1, so the denominator got smaller, so the fraction got bigger. So this is bigger than this, but this equals this, which we know is the harmonic series. So what have we established?
we've established this, right? We've established if we take the series n equals 2 to infinity of n cubed over n to the 4th minus 1, we know that series is bigger than this series.
But that is a divergent series. That's the harmonic series, and that series diverges. Therefore, by the comparison test, our series diverges. So that's 9 and 10. They're here to get us warmed up and to help us establish the idea of when do I want to go less than and when do I want to go greater. Okay? Less than if we think it's going to converge, greater than if we think it's going to diverge. All right, so let's clear this off.
And now let's take a look at something like problem 15, right? So it just says for the instructions, does this converge or does it diverge? You tell me. So if we look at 15, 15 is the series n equals 1 to infinity of n e to the minus n.
Right? Now remember, the title to this section is the integral test and the comparison test. We've seen the comparison test in action in the last 2 problems. This looks like one of those things that we integrated back in the day using parts, doesn't it?
So we're going to think about doing this with the integral test. Okay. So what does the integral test ask?
Well, the integral test asks a lot, doesn't it? The integral test has 3 hypotheses.
First, we have to show positive terms. Second, we've got to show continuous function. And third, we have to show decreasing.
Okay, this is what we have to show. Decreasing, we're generally going to do that with the derivative. Show that it's less than 0. Okay, so when we come over here, we take a look at this, right?
Are the terms positive? Well, what do we have? We have n divided by e to the n. Right, that's what this is, e minus n. This is always positive when n is greater than or equal to 1, which ours is.
Right? Because e to the n is always positive. The graph of e to the x is always positive. It's in quadrants 1 and 2 only. And n is going to be positive as long as and it's positive. In this case, because we're working with series, n starts at 1, so it's positive.
So we've got that one. Continuity. All right, so here we're going to consider f of x equals x over e to the x.
Right?
This is a fraction. E to the x is always defined. Because when is a fraction going to lose continuity, right? It's going to be discontinuous. A fraction is only going to be discontinuous if the denominator is equal to 0. And e to the x is always defined and never 0. Right? The graph of e to the x goes like this.
It doesn't touch 0.
So f of x is continuous. Now we got to worry about decreasing.
Right? So how are we going to show it's decreasing? Well, we're going to take the derivative and set it equal to 0. Set it equal to 0. We're going to take the derivative and show that it's less than 0. So if we take the derivative to this, right? So if we take the derivative of x e to the minus x, what do we get? Well, we use the product rule. We get the derivative of x, which is 1. So we just get e to the minus x plus, and here we get the first term, which is x, times the derivative of the second term, which is e to the minus x, times the derivative of minus x, which is minus 1. So if we factor out an e to the minus x, we're left with 1 minus x, which, if you prefer, is 1 minus x over e to the x. Now we have to show this is negative. And it is, of course, whenever x is greater than 1. Well, our x starts at 1, right? So this turns out to be, at 1, it turns out to be 0, but everywhere else it turns out to be negative. So this function is decreasing. So we've satisfied the conditions for the integral test. Now remember, the integral test says if we look at the integral from, in this case, 1 to infinity of x e to the minus x dx, the behavior of this integral is going to determine the behavior of our series. If this integral converges, our series will converge. If this integral diverges, our series will diverge. Now, to do this integral, of course, we go here. The limit as t approaches infinity, the integral of 1 to t x e to the minus x dx, because it's an improper integral. And now we're going to use parts. This is a parts problem. So we're going to come over here and we're going to go, well, u equals x, dv equals e to the minus x dx. When we take the derivative here, we get dx. We take the integral here and we get v equals, the integral of e to the minus x is minus e to the minus x. And so now we know what this is equal to. This is equal to the limit as t approaches infinity. We integrate this by parts. So we get uv, which is going to be minus x e to the minus x, plus, it's really minus, but I'm factoring in this negative right here, the integral of v du, right? So that negative made this a plus, and we have e to the minus x dx here. Now this is evaluated between 1 and t. So what do we get here? Here we get, remember, we're taking the limit as t goes to infinity. Here we have minus x e to the minus x. Here we have the integral of we have the integral of e to the minus x, which is going to be minus e to the minus x. And we're going to evaluate that between 1 and t. So if we clean this up a little bit, we can take out, we have the limit now, as t goes to infinity. And now we have, let's take out a negative, e to the minus x, right? That's going to be down here, isn't it? Because e to the minus x is e to the x in the denominator. And I pulled the negative out as well. And on the top, we have 1, right? 1x here and a 1 here. So we just have x plus 1. And we're evaluating this between 1 and t. Okay. Now, this becomes, of course, t plus 1 over minus e. So let's go ahead and plug everybody in. We put a t in here, right? So we have t plus 1 over, we'll put the negative out here, e to the t. And then we have minus, but we also have a minus here, so we have plus, and we put a 1 in here, and we get 2 over e to the first, right? Now remember, this whole thing is as t goes to infinity, right? That's what we're going to do here. T goes to infinity. Well, this is infinity over infinity. This is just a constant. So as t goes to infinity, we're going to have to take this by L'Hopital's rule, right? So what do we have over here? We have the limit as t goes to infinity. And we have t plus, we'll put the minus out here. We have t plus 1 over e to the t. Now to do that, we're going to have to use L'Hopital's rule, which means we're going to get minus the limit as t goes to infinity. The derivative of the top is going to be 1. The derivative of the bottom is going to be e to the t, and this is going to equal 0. So this piece is going to be 0. This piece is going to be 2 over e. So the answer is going to be 2 over e, which means this integral converged, right? Didn't equal infinity. So that integral converged, and because it converged, our series converges by the integral test. Okay, so that's number 15 from 8.3. So it converges by the integral test because our integral converged to 2 over e. All right. Okay, so that's 15. Let's go ahead and erase this one now. That one had everything. We had L'Hopital's rule. We had a improper integral. We got to take the derivative and see if the function was increasing or decreasing. We got to talk about continuity. That was a little bit of everything, wasn't it? All right, so let's take a look at 19. We'll do that one next. 19. Again, it's just converge or diverge. This is the series. So it's the sum n equals 1 to infinity. And we have cosine squared n over n squared plus 1. So we look at this and we're like, well, I do not know how to integrate this, right? We don't know how to integrate this. So we're not going to try to integrate this. We're going to try to work with the comparison test. But we don't have any inherent idea on how this is going to work, do we? So what are we going to do? We're going to write this down. And we're going to ask ourselves, we're going to look at the functions, we're going to ask ourselves, is there anything we know for sure? Well, cosine squared, isn't it? We know cosine itself, right? Cosine itself lives between -1 and 1. But when we square it, cosine squared lives between 0 and 1. So this could be 0. It could be somebody like a half. It could be somebody smaller than 1. So this is always less than or equal to 1 over n squared plus 1. Because cosine squared n is less than or equal to 1. So the denominator is the same. So since the numerator is less than or equal to 1, this fraction is less than or equal to this fraction. But this looks a lot like those problems 9 and 10 we took a look at. We've added something to the denominator. We've made it smaller by adding something to the denominator. This is less than this. And that's our friend, the convergent p-series, right? This is a convergent p-series. Since p equals 2, which is greater than 1. So what do we have? We have our series is less than or equal to this series, which is a convergent p-series. And so our series is less than or equal to a series which converges. Therefore, our series also must converge. That's the comparison test. So that was a lot nicer than number 15. So that was number 19. Let's take a look at 22. 22. Ooh. Okay, so this is n equals 1 to infinity. We have 4 plus 3 to the n over 2 to the n. All right. So what are we going to do here? Well, if we take a look at this, we can split this up, right? We can split this up. We can write this like this. N equals 1 to infinity, 4 over 2 to the n, plus n equals 1 to infinity, 3 to the n over 2 to the n. Well, we can do that. Can we bring this 4 out front? Yeah, we can do that. This, right? This is really this, isn't it? Now, if we take a look at those two series, those are two series that are geometric. If we write down the first term here, right? The first term here, if we just write down a few terms, n is 1, we get a half. N is 2, we get a fourth. N is 3, we get an eighth. This is geometric. We multiplied by a half. We multiplied by a half. What do we get over here? Well, when n is 1, right? When n is 1, we get 3 halves. When n is 2, we get 9/4. When n is 3, we get 27 over 8. Here, we multiplied by 3 halves. Here, we multiplied by 3 halves. So these are both geometric. So if we look at them individually, right? Let's just consider them individually. If they both converge, then we converge. If one of them diverges, we're done, right? So let's take a look at the first one. We know the sum is equal to a over 1 minus 4, right? When r is what, though?
the absolute value of R has to be less than 1. Which, if we don't like that, it means this is true, doesn't it? R has to be between -1 and 1. But what's R right here? R is 3/2. 3/2 is bigger than 1. This is a divergent geometric series. This series converges. But this is a divergent geometric series. So our series, we didn't compare it to anything. We literally worked with our series. We just attacked our series. Our series is a divergent geometric series. Okay, so that's number 22. Let me clean this up a little bit and we'll make some space here. Okay, so let's take a swing at 33. Right? Now, to do 33, it says use the sum of the first 10 terms to estimate the sum of the series. And so the series we're working with here is n equals 1 to infinity of 1 over n squared, which we know is a convergent, right? Convergent P series, because P is 2, which is bigger than 1. So this is a convergent P series. So part A says use the sum of the first 10 terms. So we put 1 in here, we get 1. We put 2 in here, we get, I can do this, 2 in here, n is 2, we get a 4, right? We put 3 in here, 1 over 3 squared is 1/9. And we're going to go all the way to the first 10 terms, right? So we're going to put 10 in here because we started at 1, then we put in 2, then we put in 3, and we put a 10 in here, we get 1 over 10 squared, which is 100. Okay. Now I already summed that up. That equals 1.55. So we came up with S sub 10, the 10th partial sum, and we said it's 1.55. Use the sum of the first 10 terms to estimate the sum of the series. How good is this estimate? All right. Now, how are we going to see? Well, we have a theorem for, right? We have a theorem over here for the comparison test. And it tells us the remainder estimate, right, for the integral test. And we could, right, we could do this problem that way, right? We could. And what does it say? It says, if we want to know what it says this. It says, if you do an integral, but you don't integrate all of it, right? Because we don't know how to integrate all of it. And if we integrate it, that's not going to be the series anyway, is it? If we do the integral from 1 to infinity of this, that's going to be all the values. 1, 2, 3, 4. That's what we want, right? We want this. We want the distinct values 1, 2, 3, 4. But if we integrate this, integrals find us the area under the curve. The integral is going to give us the value of the area under the curve. That's not going to be this. So what the error estimate says, right? It says this. It says if we take S minus the sum of the first n terms, we're going to call that, we call that a remainder. Okay. So this has a sum
because it converges, it has a sum, we don't know what it is.
So we know this equals S because it converges. And we know why it converges. We know it converges
Because it's a P series and P is 2, and that's bigger than 1. I don't know what that is. I don't know what S is. But if I take S and I subtract S sub 10, what's left is going to be R sub 10. Okay, it's going to be the error, if you want to think about it that way, or the remainder, if you like that phrase better, between the actual sum and our sum. And the question 33 is asking is, how good did we do? Right? How good did we do? Well, we have a remainder estimate for the integral test, right? It's in the book. And it tells us this. This is what it tells us. It says this remainder, R sub n, is less than or equal to this. And greater than or equal to this. That's a very bad infinity, isn't it? So the remainder is bounded below and bounded above by 2 improper integrals. For us, we know what n is, right? N for us is 10, so this is 11 down here, and this is 10 here. So our error is stuck between these two values. Now, we can find both of these, can't we? We can integrate this. If we wanted to do this integral, we would write this, wouldn't we? The limit as t approaches infinity, the integral 10 to t, and f of x for us is going to be 1 over x squared dx. Now, if we integrate, that's x to the negative 2, right? We add 1 and divide. We add 1, so that's going to give us x to the negative 1. We divide by negative 1. We get minus 1 over x, don't we? So this equals the limit as t goes to infinity, right? We integrated this. We got minus 1 over x evaluated between 10 and t. So we plug them in. We get the limit as t goes to infinity. We put a t in here, minus 1 over t, minus from the fundamental theorem of calculus. Then that minus makes it a plus 1 over 10. Well, as t goes to infinity, that's 0, right? 1 over infinity is 0. So this thing equals 1 over 10. So this is 1 over 10. Now, nothing's going to change if we make this an 11. So this is 1 over 11. So what do we know? We know that R sub n is bounded below by 1 over 11, which is smaller than 1 over 10. So that works out really nice. Now, I didn't bring a calculator up here. Well, I guess I have my phone. So let's see if we can so on this side, we get 0.090909. And on this side, we get 0.1. Okay. So we know that we're bounded between those two values. Now,
question asked us. Use the sum of the first 10 terms to estimate the sum of the series. So we know, right, based on our arithmetic up here, that if we move this over here, we would have S is equal to S sub n plus R sub n, right? Now, we don't know what R sub n is. We know R sub n is between these two numbers, right? So we could say that the sum is approximately equal to S sub 10 plus R sub 10. Our S sub 10 was 1.55, and R sub 10 is a number between here and here, right? And we could take the average of these two numbers if you wanted to do that to find the number that's between there. We can just add those two things together, right? I mean, that doesn't take a lot of work. Plus 0.1. And then divide that by 2. And we get R sub n is approximately equal to 0.09545, repeat. And so we could add this to here and come up with an approximation to S. Now, part B is just doing the same thing again. Part C says find a value of n that will ensure the error in your estimate is less than point. So we want our error to be less than 0.001. They want us to find n, right? Now to do this, there's an example that does this for you in the book, right? We can take a look at example 6. I mean, they do this entire calculation for us. In example 6, their error estimate is 0.0005, but the same exact thing. And so what do we know, right? We know that for us, the size of our error, right? We know our error, R sub 10 from here, R sub 10 is less than this, which we found to be 1/10. So what do we know? We want to find n to make it at least less than this, right? So we know R sub n is less than or equal to the integral from n to infinity of f of x dx. And we took that integral, right? We came up with this for that integral, didn't we? Which is just 1 over. We're not using 10 here. This is n. So this would be n. So this would be n. So we just came up with 1 over n because this one went to 0. And that is not a 10. Now it's an n. So we have 1 over n. And we want this to be less than 0.001. Now we can solve that inequality, multiply over here by n. And we get 1 is less than 0.001 n. Divide over here by this. And so we get n has to be greater than, right? 1 divided by that is going to be 1,000. So we get n
has to be greater than 1,000. So n would have to be greater than 1,000. So n is going to have to be 1,001, right? 1,001. Okay, so that gets us going on 8.3. I'll go ahead and end this now. Hopefully that's enough to get you off and running.